In this example, we're going to be working with pistons. And before we get started, I want to show you a little bit about kind of how these work. So on the left here, you can see a picture of one, but it's more helpful to look at an animation. So I'm going to pull that up now. So this is kind of how they work. You have this little thing at the bottom. I don't really know what they're called, but um, it kind of moves around in a circle, and the piston itself, which is the cylinder, moves up and down. So let's go back to here. So you can kind of envision what that would look like in this picture. So the problem itself says that a piston engine is the most commonly used engine in the world. The height of a piston over time is modeled with a sine curve, and they just give us the general form of a sine curve. A certain piston reaches a maximum height of 5 centimeters and a minimum height of 0 centimeters. It completes 3 rotations every second. And we want to write a sine function. All right, so you kind of get a hint with all the different letters written in here, so we know which components we have to think about. And so let's write down the information we're given. So the maximum is 5, and the minimum is 0. Frequency is equal to 3. And that is what we're given. So it's tempting when you see maximum height of 5 centimeters to immediately assume that is amplitude. But amplitude, remember, is the distance from the midline, either up or down. So it's not the maximum, it's just the distance from the middle to the top or the middle to the bottom. So in actuality, the amplitude is going to be the average of the maximum minimum, or just the number that's in the middle. So the amplitude is going to be 2.5. And then our midline is going to be that, well, I should have done this in a different order. So the first thing you would do is find the midline, which is the number that is directly in between the maximum and minimum. And then you want to find, here, let me draw it out. So the midline is going to be this line right here. So now that we found the number in the middle, we want to find the distance from that midline to the peak. And then so the way to do that would be 5 minus 2.5. So I just took the maximum because I think that's easiest, and that's going to be 2.5. So that has to be our amplitude. Okay, and then we found letter A. We still need to get letter B, and we found letter D, and there's not going to be any phase shift, so C is just going to be 0. But let's go ahead and work with this frequency. We know that period is equal to 1 over frequency. That's the relationship between period and frequency. You can just do 1 over the other, and then you're able to get the other one. So then we're just going to do 1 over 3. And remember, period is usually in a unit of time, but it could be angle as well. So this is going to be in seconds. But we're not done yet because we have period, but we need to get B. And period is equal to 2 pi over B. That's how they relate. So we can say 1/3 equals 2 pi over B. And then we can kind of just switch them. So B is going to equal 2 pi over 1/3, which is the same as 6 pi. And now we have everything we need to build our equation. So let me do it in purple. So y is going to equal the amplitude, which is 2.5, times sine, and then we need our b, which is 6 pi. There's no phase shift, so we don't have to worry about that. And then this time we do have a vertical shift. Anytime the midline is not 0, then there's a vertical shift. So we have to add a 2.5. Okie dokie. Let's move on to part B. This part is asking which parameters, or maybe just one parameter, would be affected as the piston moves faster. So this is an interesting question, and the way that I approached it is by just thinking about in general, you know, all the characteristics we know, frequency, period, amplitude, whatever, the first thing that comes to mind that I know would change, and that thing is going to be frequency. Because if you think about it, as the piston is moving faster and faster, it's going to be moving up and down much faster. And so the amount of cycles you get in 1 unit of time is going to increase. And it's not asking for a direction or anything like that, but hey, why not? Let's add it. So frequency is going to increase. Okay, and then so that's going to lead me to wonder, well, what does that impact? We know that frequency and period are related, and they're inversely related. So if frequency increases, that means our period is going to decrease. So the amount of time it takes to complete one cycle is going to decrease. Okay, and we also know that period is related to the wave number, b. And if we look back at our equation over here, you can see that like it's kind of hard to it's kind of hard to explain, but if you increase, well, in this case we're decreasing, so if we decrease the period, we have to think about what must have happened to b. And if you divide by a bigger number, that's going to cause a decrease. So if period is decreasing, that means b is going to increase. I'm sure there are other ways to remember that, but I just kind of think about if this variable did this, what would the other variable had to have done? Okay, and then so let's look at these other parameters and see if those would be affected. We never had a phase shift, so definitely not that. Amplitude could be kind of tricky, but when you think about it, this rod right here is just moving along this circle. So it's not like it's moving in a wider circle or that, you know, nothing like that is changing. It's just doing it faster. So amplitude is not going to be affected. And because that maximum and minimum height is not being affected, midline's not going to be affected. So really, it's just going to be our wave number. Okay. This last part is kind of crazy, so I'm just going to go ahead and record it in the next video.